Hey, Chemistry Coach coming at you. And in the last video, I promised we would look at the method of initial rates, which is our main way of determining those exponents in a rate law. Remember, you have the rate law is the rate times equal rate R is equal to the rate constant times the concentration of your first reactant raised to some integer m times the concentration of your second reaction raised to some integer n. And if you had more reactants, right, you'd have to use m and n and o and p, whatever. But typically, we'll just leave it as 2 reactants max, right, either 1 or 2 at this level, right? And our goal is to figure out what those exponents are, those integers m and n, which are not necessarily equal to the stoichiometric coefficients. So that's what the method of initial rates is, by far the most common one. And I know for my class, we're going to do that in the lab. Yeah, for the kinetics lab. It's kind of cool. Takes a while, right? It takes a while to run it. Lots of calculations. Pretty crazy. But all of that you can determine m and n. Of course, we're not going to get, perfect integers in lab. You might get like a 1.93, right? It's with an experimental error, it's close enough to 2 for our case, right? A 0.12, yeah, that's probably close enough to 0, right? So that's our goal. So here's the general process, and then we'll do some examples and show you then once we have m and n, what can we do, right, to determine the rate constant, right, or some other things. The fun stuff we're getting to. All right, so essentially we're going to do 3 experiments, maybe more depending on how many reactants we have. But if you have 2 reactants, in essence, you need to do 3 separate experiments, right? Unless you do some fancy pants stuff in lab. First one, we're just going to get some initial concentration A and initial concentration of B. Pretty easy to measure those, right? And then measure the initial reactant rates. That's why it's called the method of initial rates, right? We're doing it initially. Boom, right? Remember with the graphs, we showed you do the tangent line, right? When t equals 0, boom, we can get that slope that's equal to the rate. So we can measure rates and concentrations in lab. Pretty easy to do, right? So we're going to do that for initial concentrations. Now we're going to manipulate things. Let's do a second experiment. Let's take one of the reactants. Let's start with reactant A. Let's double that. Now you could triple it, quadruple it, but the math is easiest if you just double it, right? It takes less of the, it costs less money because it's less reactant that you're using up, right? So let's double species A and hold B constant. And if there's more reactants, hold all of the others constant. And we're just going to focus on species A, reactant A. Let's double that one. How does the reaction rate respond to that? Oh, so we're going to double A, hold B constant, and remeasure the rate. Does the initial reaction rate change when you double the concentration of species A, reactant A, right? I'll show you how to do that. That's going to allow us to determine the exponent m, right? The order with respect to species A. Ooh, it's actually you can kind of do it in your head sometimes if you know what you're doing. But what about species B? Okay, so now we have to do a separate experiment for the other reactant. We're assuming 2 reactants in this case. Well, in that case, let's double species B, but hold A constant, right? Or everything else will remain constant. So all we're doing is doubling species B. How does the reaction rate respond to that? And we can go remeasure the reaction rate. We can remeasure all of the concentrations. And from that, I'll show you how to determine the exponent n, the order with respect to species B, reactant B. Woo! Right? That's the essence of it, right? Measure the reaction rate for some initial reactions, some initial concentrations. Double one of them, measure the reaction rate. Double the other one, measure the reaction rate, of course, holding everything else constant. So again, we're focusing on one reactant at a time and doubling it and see what happens. Let's look at how the math works out. And from that, how do we determine m and n? Okay, here's the essence of what you're going to be looking at. And again, some of you might be able to just see this in your head once you get this. Once you get it, it's really easy. All right, here's this rate law. We're trying to determine m and then n. That's our goal. And remember, we're doing 3 experiments. First one, we're just having some initial concentrations of A and B and measuring the initial reaction rate, right? Second one, we double A, hold B constant, measure the new reaction rate. Third experiment, double B, hold A constant, measure the new reaction rate. We're essentially going, how does the reaction rate change or respond after we double one of the reactants holding everything else constant? Method of initial rates. So double one of the concentrations of one of the reactants, hold the rest constant, and look at the effect on the rate. So what are we going to do? This is what you're going to calculate. You're going to look at some data. You're going to have those 3 or more experiments, right? And you're going to look at the reaction rates. And you got to look and see, okay, which one of these 2 experiments has all of the reactants constant except one that we doubled it. And then you look at those reaction rates. And then just measure the ratio, right? So we're going to take the rate, the reaction, the initial rate, after we double either species A or species B. It's the same calculation. Just going to use, right, whatever data you need. And then divide that by the initial rate before you doubled that, right? So kind of final after initial, the second experiment over the first. But you're going to have to look at it and go, okay, so maybe in the first experiment, that's before we double anything. In the second one, we double A and hold B constant. So you take the rate from the second experiment divided by the rate from the first experiment. But maybe we're looking at species B, and maybe we need experiment 3 for that one, where we hold A constant and double B. So we take the rate from experiment 3 and divide that by the rate from the first experiment where we hadn't doubled anything. You just look at, usually you're provided a data table and you can kind of see it. And I'll do an example where you'll be like, hopefully you'll be like, So you're just calculating the ratio of these initial rates after you double one of the reactants. All right, well, in this level of class, we're gonna have 3 scenarios, okay? So with respect to the reactants A and B, it'll either be 0th order, 1st order, or 2nd order. We're not gonna go beyond that. All right, so it's one of 3 options. So here's the impact on this ratio of the rates, okay? So case A, B, and C in red. What if that ratio you calculate is equal to 1? Whoa, that would mean you've got the same number on top and the same number on the bottom, right? So if we double A, for example, and we get the exact same initial rate as we did before we doubled it, whoa, that gives you a value of 1. You can see that on the data table. Well, if that's the case, since we doubled it, that's the same as 2 to the 0 power, or 2 to the n, right? Essentially, we're looking at if you double this reactant, the impact on the ratio of these initial rates will be 2 to the nth power. We're after that n value. Or, that would be if it was B. It'd be m if it was A. Whatever that exponent is in the case that you're looking at. Right? So 2 to the 0th power would be 1. So if the ratio of these rates is 1, right? That means that you could double it, triple it, whatever. It's not going to change the rate at all. It's independent of that. So 2 to the 0 power, 2 to the n, right, is 1. So in that case, that exponent must be 0. The rate stays constant, so it'd be 0th order. So if that happened with A, say we doubled A, holding B constant, and the rates were exactly the same, the rate stayed constant, that's 0th order with respect to A, right? So in that case, M would be 0. But what if the initial reaction rate actually changes? Say we double A, hold B constant, but the rate doubles, right? So you take the rate after doubling species A divided by the rate before, and you get a value of 2. So in that case, the initial reaction rate is twice as fast. It doubles. Well, 2 is the same as 2 to the 1st power, or 2 to the n. So in that case, the exponent would be 1. That means it's 1st order with respect to that particular reactant. For example, if I take the initial concentrations of A and B and measure the reaction rate, and then I say hold A constant and double the concentration of B, and the reaction rate doubles, right? Well, that divided by that would be 2, which means 2 to the 1. That means it's 1st order. So when you have a situation where it's 1st order with respect to a reactant, you double that reactant, you're going to double the reaction rate, holding everything else constant. All right. Last scenario. Let's say, for example, we take initial A and B and measure its reaction rate. That's usually experiment 1. Let's say we hold B constant and we double A. All right. And the reaction rate goes up 4-fold, right? So it's, the rate after doubling divided by the rate before doubling is 4. Oh, well, that's 2 to the 2nd power. 2 squared is 4, or 2 to the n. In that case, n is equal to 2, so that would mean it's 2nd order with respect to that reactant. The reaction rate quadruples. So you can kind of see that in your head. You go, okay, holding these constant, if I double that one, oh, it doubles. Oh, okay, it must be 1st order with respect to that reactant. Or you look at the data table and you go, okay, so holding everything constant, but I double that one, oh, the reaction rate quadruple. Boom, it's 2nd order with respect to that. And you can either just memorize that, or you can just see it in your head, right, using this. Let's do an actual example. I'll write up a data table. See if you can do it on your own right? And you might, at least in my class, show the calculations, at least calculate the rate ratios, right? After doubling divided by before doubling, and just show me that that's either a 1, 2, or 4, or pretty close to those, right? If you get anything besides those, you messed up somewhere at this level. Let's do an example. All right, here's our example, and I just made this up. This wasn't done in a laboratory, so don't go check these numbers. You're going to be like, that's not what I got in lab, if you can even do this in lab, right? So we no longer have a generic reaction, right? So let's take some xenon gas, react it with some fluorine gas to get a xenon pentafluoride, right? Balance that, so we get 2 moles in front of the xenon, 5 in front of the fluorine, and 2 in front of the xenon pentachloride, right? And we want to figure out what the rate law is for this. Well, let's say we go into the laboratory and run some stuff. Theoretically, these are just made up numbers, right? Again, we got 2 reactants, so we need 3 experiments to be able to determine the orders with respect to the individual reactants. So let's say experiment 1, we take some xenon, and let's say 477 torque. We use a pressure in this case, right? You could do molarity, you could do whatever. The units aren't important at this point. So let's say we take 477 torque. And let's say we make the fluorine 825 torque and measure the initial rate of that reaction. And let's say we get 3.011 times 10 to the minus 8 torr per second or something like that, right? All right, no big deal. And let's say we do another experiment where we make the xenon 954 torr. So we double the xenon, but we hold the fluorine constant at 825, right? So we're doubling one of them, and look at the impact at the initial rate. Okay, so we get 6.048 times 10 to the minus 8th, right? In this case, torr per second or something. All right, so let's do a third experiment. Now, in the second one, we doubled xenon holding fluorine constant. Now, in this third one, we need to hold the xenon constant and double the fluorine. Okay, so we hold the xenon constant as the same as experiment 1. So we hold that constant at 477, right? But we take the initial fluorine from experiment 1 and double it to 1,650. I just put that decimal point there to make that 0 significant, not critical. And we get an initial rate of 1.189 times 10 to the minus 7th. Okay, so we've got all the data we need. So we're going to break this up into several factors. A, what is the order with respect to reactant? I was going to say reactant A. We know what that is in this case, to xenon. So this will be the overall rate law, right? We're going to our goal is to determine M and N. So the rate is going to be equal to the rate constant times the concentration of xenon raised to some integer M, and that's not necessarily going to be equal to 2, right? Times the concentration of the other reactant fluorine raised to some integer N, which is not necessarily going to be equal to 5. Probably won't be. Could be, but probably won't be. That wouldn't be any fun on a test, right? It'd be too easy. So now what we have, in order to do this, we have to go, okay, so if we want to determine xenon, right, and we want to figure out what M is in that case, we need to hold the fluorine constant, don't we? So let's take a look at 2 of these 3 experiments where we hold fluorine constant. Well, that'd be experiments 1 and 2, right? So go ahead and go ahead and do this. See if you can do it on your own. So we're not even worried about experiment 3 for this one. Just focus on experiments 1 and 2, where fluorine is held constant. Remember, take the ratio of the rates, right? So take the rate after you double it, divided by the rate before you double it, and you're going to get a value equal to one of those ones I did on the prior board, 1, 2, or 4. And from that, you can determine if it's 0th order with respect to xenon, right? In this case, M would be 0, or first order with respect to xenon, M would be 1, or second order with respect to xenon, M would be 2. Now remember, if it's 0th order, the reaction rate, the initial rate won't change. Well, it changed, didn't it? Right? You can see it, right? If it doubles, it's first order with respect to that reactant. If it quadruples, it's second order. So you can kind of just see with your eyes, it kind of looks like that doubles. And doubling would be 2 to the 1 So M would be 1. So you can kind of do it in your head, but go ahead and do the calculations real quick. I'll pause this, put the calculations up on the board, and you can kind of see how you can calculate it, but also see it in your head. And then you can do the same thing. Obviously, part B is going to be what's the order with respect to fluorine. You can do the same thing. Let me write this up. All right, did you get what I got? All right, so let's take the rate from experiment 2, that initial rate, divided by the rate from experiment 1. Let's look at the impact on that rate for doubling xenon in this case. Well, take 6.048 times 10 to the minus 8 torr times second, divided by 3.011 times 10 to the minus 8 torr times second. Times second to the minus 1, or torr per second. And like I said, the units don't really matter because they're just going to cancel out. It does not matter what the units are on the rate, regardless. It doesn't even matter what the units are on the concentration. Right? Well, I get 2.00863, good to 4 sig figs, right? Well, that's pretty darn close to 2, right? So that means when we hold fluorine constant and we double xenon, the rate doubles, right? Now, you could just memorize that means that's a first order with respect to that reactant. Or you can say, well, 2, right? That's the ratio, is equal to 2 to the first power, which is 2 to the m, so m is 1. Right? Because we doubled it. Now, if you triple this, we would go 3 to the m power if you triple the concentration, but it's easier just to double it, right? So 2 equals 2 to the first power, 2 to the m, so that means m must equal 1. So that's the order with respect to xenon, so it's first order in xenon, or with respect to xenon. Let's do the same thing. I'll leave this data table up. I'm just going to erase this and put B. You can sense what's coming. What's the order with respect to fluorine? If you're on top of your game, you could get this done before I finish. I pause this. Well, actually, you can't because I'm going to pause it, write it up on the board, and be done in like a millisecond according to your time. Let's see how fast you can do it. See if you can get it on your own and see if you can get what I got with respect to fluorine. All right, let's see if I got any mistakes on here. Hopefully not. If I make a mistake, let me know. I don't know how you let me know after you watch this video. All right, anyway. So we're trying to figure out, oh, this should be B now. So part A, we figured the order with respect to the first reactant, xenon. All right, you don't have to go in the order I did. You could have done fluorine first. It really doesn't matter. But now we got xenon. Let's do fluorine. So what is the order with respect to fluorine? Well, of course, obviously, in that case, we're going to have to hold xenon constant, hold everything else constant, and double fluorine and measure the impact on the reaction rate. Does it stay constant? Does it double? Or does it quadruple? 0th order, first order, second order. You just have that memorized. It's really easy to go. Well, let's take a look at the experiments. You can take any experiments, but obviously the only two where xenon's held constant is experiment 1 and experiment 3. So xenon's held constant at 477 torr. And in experiment 1, we take fluorine at 825 torr and double it to 1,650. So experiments 1 and 3 are what we're focused on. So let's take the rate from experiment 3, 1.189 times 10 minus 7th torr per second, right? The rate of 3. Divided by the rate from experiment 1, 3.011 times 10 to the minus 8 torr per second. Units cancel out. So again, the units really don't matter in that case. Let's take that ratio, and I get 3.94885, good to 4 significant digits. Well, that's pretty darn close to 4, so I'm going to round that to 4, approximately 4. So the rate, when I double fluorine, right? Remember, these are not actual data, right? I just made this up. If we hold xenon constant and we double fluorine, the reaction rate quadruples. And you just memorize that, meaning it's second order with respect to that species. Or you can say, okay, well, 4 is equal to, because we doubled it, 2 to the second power, 2 squared, which is 2 to the n. So in this case, n must equal 2. That's the order with respect to fluorine. So it's second order in fluorine. First order in the xenon, second order in fluorine. So obviously, it hopefully makes common sense. Now that we know all of the individual reactant orders, we can calculate the overall reaction order. That's going to be part C. You should be able to do that. Just add them together. Tough math. So let's do that. Figure out the overall reaction order for me. Let's do that next. I'm going to pause it and get that up on the board. Hopefully this didn't make you sweat too much, right? So let's take C. I just left everything else up there. Let's take C. What is the overall reaction order? Because we can do that now. We know what M and N are. Overall reaction order is just the sum of all those exponents. And if you had 3 reactants, you'd have to do m plus n plus o or whatever you did it, right? So we know the order with respect to xenon in part A was 1. It's first order with respect to breakfast, xenon. And n, it was second order with respect to fluorine. So 1 plus 2, just take the non-rounded. We want those to be integers, so you're not going to take the non-rounded values. Just take the integers. Last time I checked, I need my calculator for this, right? 1 plus 2 is 3. The overall reaction order is 3, or in kinetics lingo, it's a third order reaction. And we're really after that. That's something we're going to do later with integrated rate equations as well. We're after, is that an overall, is that a 0 order reaction? Is that a first order reaction? Is it a second order reaction? Is it a third order reaction? That can tell us a lot of information about how things are happening, right? So that's not too bad. That's my favorite question of them all. Well, now that we know all this, we can write the rate law. We wrote the rate law generically with m and n, but now let's write the rate law for this reaction with the actual exponents. And instead of writing m, write the value for m, right? Unless it's a 1, right? Then you don't write anything. It's just assumed. If it's a 0, you just eliminate the entire reactant. It's kind of nice. And then we know what n is, so write the value then. So do that for part D. Write the rate law for this reaction, the specific one, not the generic one. Let's go ahead and do that. I'll be right back. Should be pretty straightforward at this point, right? This actually, once you get the method of initial rates, you're like, yeah, slobber on the mouth. Please give me one of these on the exam. Please, easy points, right? You just read it right out the data table. Now, figuring all these out in the lab, that's a whole different ballgame. All right, so what's the rate law? Well, we know generically the rate law is the rate constant times the concentration of the first reactant raised to the power of m, some integer, times the concentration of the second reactant raised to the power of n. This is if you have 2 reactants, of course. Well, we know m and n. That's why we did the method of initial rates in the first place. So the rate law will be the rate, overall rate of that reaction will be the rate constant, which we don't know yet, times the concentration of xenon raised to the power of 1, which we don't write. And it's not wrong to write it, but it's redundant, and chemists go, we don't like that, right? We don't like writing that 1 in there. We go, it just drives us nuts. It's not wrong, but it drives us nuts. So if you want to drive your professor nuts, put a 1 there. And then times the concentration of the second reactant fluorine. Well, it was second order with respect to that. So we put the little 2 there. That's why it's 1 plus 2. Third order. Now, obviously, the coefficient in front of xenon's a 2. Well, the exponent's not a 2, it's a 1. And the coefficient in front of the fluorine's a 5. The exponent's a 2, not a 5. That's why I keep saying over and over and over that m and n are not necessarily going to be equal to the balanced stoichiometric coefficients, right? From the balanced equation, right? It could be, but more often than not, it's not going to be. All right, so that's A, B, C, and D. And now we can extend this one more. We haven't done this yet. Now that we know everything in the rate law, now remember, we have rates from the data table. We have concentrations from the data table. Oh, wait a minute. Now that we know m and n, we know m, we know n, we know A, we know B, we know R, we know everything except K. And you can pick experiment 1, 2, or 3. It's not going to matter. It might vary a little bit based on, experimental error and whatnot. But you can take any one of these experiments. I always just do the first one. That's totally up to you. Door number 1, door number 2, or door number 3. Doesn't matter. Calculate the rate constant. Let's do it. Determine the rate constant. Take any one of these. I'll take 1 if you want to calculate ahead of time so you can get the exact same answer I do. But if you did 2 or 3, you're going to get pretty darn close to what I got, within, the last significant digit probably. So do it. Let's do part E. Calculate the rate constant K. Do that for me. All right, getting a little squishy on my board, but I need to leave that data table up there. So it's like I'm doing a competition with one arm tied behind my back. Half my board always has to be left with that data table because you need it for all of these, right? So to be able to determine the rate constant, I need data from the data table. I'm just taking experiment 1. So calculate the rate constant. That's K, of course, little k. Capital K is going to be an equilibrium constant later. So make sure your rate constants are little k, not the big K. So I'm just using experiment 1, but it doesn't matter again, all right? If you use 2 or 3, you're going to get pretty darn close to what I got. Well, we know the rate law was R equals, the reaction rate was K, the rate constant, times the concentration of xenon raised to the power of 1, times the concentration of fluorine raised to the power of 2. All right, well, let's just rearrange that. We're isolating K, right? So let's just divide both sides by the concentration of xenon and the concentration of fluorine squared. So the rate constant should be the rate R divided by the concentration of xenon and the concentration of fluorine squared. Don't forget that squared there. Oh, well, I know R is 3.011 times 10 to the minus 8 torr per second. I'm just times seconds to the minus 1. Or you could write torr over seconds, whatever you want. Concentration of xenon in experiment 1 is 477 torr, right? I don't know what my computer just did there. It keeps trying to load something. I don't know if you saw that. That was kind of weird. So that I just put 477 torr right down there, right? Whatever the units are. And then fluorine in experiment 1 is 825 torr. So I did 825 torr squared. You're squaring the 825 and squaring the torr, right? The units in there. Because we're going to find out the units of the rate constant really determine the overall reaction order. 0 order, first order, and second order reactions, which are going to be the main ones we deal with integrated rate equations later, have very specific units for the rate constant. So if you know the units of the rate constant, you can just go, oh, that's a second order reaction, or that's a first order reaction, right? But in this case, we have a third order reaction, right? So those units, we're not going to be dealing with those later. It gets a little too complex. You can go to graduate school if you want to deal with that. All right, well, I got 4 significant digits in R, 3 in the concentration, so I'll end up with 3 significant digits in our rate constant. Let's take a look at units here. Well, I see torr here, torr there, so the torrs cancel out there, but not the torr squared. So we're going to get inverse torr squared, inverse seconds. And you can either just write torr squared in seconds in the denominator, or you can just multiply it by torr to the negative 2, seconds to the negative 1. So it's inverse concentration squared, inverse time, whatever those units are for time and concentration. Well, if I run those numbers, I get 9.2743 times 10 to the minus 17th torr to the negative 2 times seconds to the minus 1, or you can just put the torr squared and the seconds in the denominator. Good to 3 sig figs because of the concentrations. That rounds to 9.27 times 10 to the minus 17th over torr squared a second, or times torr to the minus 2 seconds to the minus 1. That's how you do that. This is how we do it. Now that you see it, should be pretty straightforward for you to do any of these. Right? And again, for my class, we're going to measure this data table in lab, and we can do all this later. That's the method of initial rates. Rock and roll. Let's get into some harder stuff, integrated rate equations next. You guys rock.